So the recording has started?
Yes, yes.
Okay. Yeah, so in case you want to follow along with the examples that I'll present in the second half of this talk, it's probably a good idea to install these packages while I'm giving a brief background, and so that can run in the background, and then you're all good to go. Most likely you have some of the packages already, Tidyverse or SF. Probably you don't have AMT, but running that should install all of them. Okay, so what I planned for today is to give roughly 15 to 20 minute talk about step selection functions, and I'll try to clarify what that is in a minute. And then have a roughly 40-minute walkthrough through some R code, how you would actually apply this to telemetry data. Maybe just before I start, a few words about my background. So I have a degree in ecology as an undergraduate, and then I have 2 postgraduate degrees in GIS and statistics. I did my PhD on methodological aspects of movement ecology. And I did my PhD, and I'm still stuck to the University of Göttingen, and I work there as a researcher now. And my research interest is mainly movement ecology, but also I'm interested in other quantitative aspects of statistical ecology. And if I work with applied data, except for this workshop and the previous one, it was always terrestrial mammals. So I fit the required profile quite well because I don't know very much about fish. Okay, so I was asked to talk a little bit about step selection function. And now step selection function is one particular method to assess habitat selection. It's always better to call it resource selection, because it doesn't have to be habitat, it could be other resources as well. And the idea is always to compare what is available to the animal and what did the animal use. And comparing this, making some inference about the availability and the use. This started to become, started in the late 60s, I presume, when the first animals were observed, also remotely observed. And traditionally, there were some indices that were calculated. You can think of it as, for example, also like a chi-square test, where you have a set of bins and you observe how many points would you expect in each bins and how many you actually observe. There was then a steady progression towards habitat or resource selection functions, and that went on towards step selection functions. So habitat and resource selection functions, the underlying statistical model became a little bit more complex, and there you have a conditional logistic regression that is being used to estimate the parameters. And for the step selection functions, then you have a conditional logistic regression. I'll hope to clarify that later. One of the big drawbacks of this method is that they're all implemented in 2D. I think I gave a talk about that at the first lake telemetry meeting, and there was no implementation in 3D, and it hasn't happened since. But I think you had some discussions about that and at this meeting, so hopefully there will be some improvement. Now, the big question that we always have is how to quantify availability. So the quantification of availability is crucial, because if you're being unrealistic to what is available to the animal, you will get very odd results, and you can basically get whatever you want. The idea is that we make availability somehow to resemble to what could the animal reach in a reasonable time frame. And this is always important to have a balance between how do we quantify availability, and what is the sampling rate of our tracking data? That is, how often do we have the position of the animal? Now, in traditional systems, probably even pre-GPS or pre-high-frequency tracking, it was often assumed that the whole home range, that is the area that an animal usually lives in, was available. And in more technical terms, what people did is, or still doing, is take all the relocations that are observed, we draw a convex polygon around them and say, well, that's available to the animal. And then we have the points where we actually observe the animal, and then we say, that's what the animal used. And then we compare this used and available, using, for example, a resource selection function. But the problem is, or what we are assuming is, that at each time step, that means the time between two relocation, the animal could basically reach any point within its home range. Now, that might be realistic if you have tracking data at a resolution of 1 point per day or 1 point per week. But if you have tracking data with every 10 minutes, every minute or so, that becomes unrealistic, even every hour. This assumption was then a little bit relaxed using step selection function. And the idea of step selection function is to define availability conditional on the position where you are at the moment. Now, this was first introduced in 2005 by Daniel Cotin using, I believe, elk movement. And the idea is, don't be too distracted here, that we have a selection function, that is this W here, given some selection coefficients. So the selection function consists of the x's that are some covariates. There could be, in a terrestrial system, it could be, for example, land cover. It could be elevation. In an aquatic system, this might be water depth. It could be something like distance to the next shore, and so on. And then this, lost my mouse. Don't know. Can you see my mouse? Or
yes, yes.
Yeah. And then we have these betas, and they kind of weight each of these axes. So we can have a positive beta for if there's a preference for a certain covariate. That means the use is more than it is available. And we would have a negative beta if there is an avoidance. That means an animal uses a resources less than it's available. And we would have 0 if the animal doesn't uses it exactly as it is available. So the S's are the position in space. And the important thing here is probably this delta t. So the betas depend on a fixed time interval. So the step selection functions require that the sampling, the tracking data is on a fixed sampling rate. So every 10 minutes, every 15 minutes, every hour. And that's one of the requirements. And the other thing that this implies is that these beta are dependent on the sampling rate. So you could get different results if you change the sampling rate of your data. And then we can estimate that. And this is just a normalizing constant. So basically, it's not that important for us here. If we want to estimate that, we can put that in a likelihood function, and we could maximize the likelihood, but we don't want to do that. So usually we use, if we just have one animal, there's the C-logit function. That's for conditional logistic regression in the survival package. In the AMT package that was mentioned already, that I'm maintaining, there is a function called fit SSF that allows you, it's a wrapper around that with some more convenient scale towards step selection. So now the idea is, or the question is probably that you're asking yourself is how to create these random points. So we first start off with regular sampling rates. So again, we have this delta t in the equation. We then create steps. That means we are converting individual points to steps, and that's nothing else than saying two consecutive points become one step, where the first point is the start point of the step, and the second point is the end point of the step. The second point, the end point of the first step is then the start point of the second step, and so on and so on. And then we have to create random steps. And the traditional formulation of step selection function was like this. So this is an animal that walks like this, and we observed step lengths, so L0, L1, L2. And then we observed turning angles. That means a turning angle here, if the animal would continue straight, we would have a turning angle of 0. And if it deviates, then this turning angle here is different from 0. So we observe step length and turning angles. And what we do then is for each observed step, so that would be that step, we take all the available steps that we have and randomly sample 10, 20 steps from that and pair each observed step with these randomly sampled steps using the step length and the turning angle of the observed steps. And we continue that for the first step and doing that for the second and the third step. When we finish that, we extract the covariate values at the end of each step. So we have observed steps and we have random steps, and we extract the covariate values. And then we fit a conditional logistic regression to estimate selection coefficients for that. So the interpretation of this parameter then can be a little bit tricky because it's all relative to each other. But using the so-called relative selection strength can be a very helpful mean for interpretation. And at the end of the practical walkthrough, I'll give an example how to do that. But just in very brief, the RSS tells us how many times more probable it is to select one out of two steps. So you have the animal has two steps available. For example, one ending in habitat A, the other one ending in habitat B. And if the RSS is 1, the relative selection strength, then the probability to end up in habitat A or B doesn't change. If this relative selection strength is greater than 1, then it's more likely to end up in habitat A than in habitat B. So the take-home point for the step selection function is that we try to constrain the availability of the animal. We have to model the availability, we have to pair each observed step with a k random steps. K could be 10, 20, 30. So it hasn't been worked out what the optimal k would be. An observed and a random step. So and one observed and k random steps, they form what is called a strata. I didn't introduce that yet, but each step forms a separate strata. Hence, we have to use this conditional logistic regression that we then use to estimate selection coefficients. Now, this was introduced in 2005. In 2009, James Forrester already noted that we kind of introduced a bias because how we sample these steps. And this led then Tal Afkar in 2016 to publish a paper where he coined the term of integrated step selection function. And the idea was, beside modeling habitat selection, also to explicitly modeling the movement of animals. And if you remember from just before, we had this equation, and we now extend this equation with this phi here. And this phi is the distance, or a function that defines movement characteristics from the position S, that's where the animal might go, to the from the position where the animal is right now. Now, this is maybe more complicated, sounds more complicated than it is, but the idea is to not only estimate coefficients for different habitat covariates, for example, land use or water depth or whatsoever, but also for movement characteristics, for example, for the step length, for the log of the step length, for the turn angle, or for the cosine of the turn angle. So the idea is, why would you do that? That's just the same as before. So remember, before we were just taking the step length and the turn angle and resampling them. But you could also take the step length here and fit a statistical distribution to these step lengths. For example, step lengths, they're continuous and positive measurements. So distributions that you could fit to these step lengths could be, for example, you could use the exponential distribution, you could use the gamma distribution, you could use a half normal distribution or log normal distribution. And then this distribution have parameters. And in the AFCAR paper, they showed that you can modify the parameters, or that the parameters of these distributions are linked to this movement characteristic. For example, if you have the exponential distribution, then the coefficient of the step length is linked to the rate parameter of this exponential distribution. This allows you to first control for the movement, so that you can afterwards calculate a selection-free movement kernel. So we usually tend to think of that these two processes, movement and selection, kind of interfere. And if you want to separate that, we will have to estimate movement and we have to estimate selection. So by including that into the integrated step selection function, we can separate these two processes. And in addition, we can say, well, how does movement change, for example, if the animal is in habitat A or habitat B? Thus, before we have to adjust our workflow slightly, and before we sample random steps from the observed step length, we replace this step by fitting a statistical distribution. Most of the time, it's the gamma distribution for step length and the von Mises distribution for turn angle. So gamma distribution for step length is just a continuous positive distribution. And the von Mises distribution, which you may or may not have encountered before, is a circular distribution. So because the turn angles, they occur on a circle, that makes things a little bit more complicated. But everything else pretty much remains the same. So we make sure our tracking data follows discrete sample, sample in discrete time with constant rate. Then we create steps again. Then we fit a statistical distribution to the observed steps and turn angles. We extract the covariates at the end of the steps and fit a conditional logistic regression here again. Now, how can we include movement in the to be explicitly modeled? So we can include habitat in the we can include just a habitat independent movement kernel. That is, for the gamma distribution, we have to include the step length and the log of the step length in the when we estimate the conditional logistic regression. And for the von Mises distribution, it's the turn angle and the cosine of the turn angle. And I'll show you in a minute how you would actually do that. Okay, then one more question that is frequently coming up. There is how many random steps do we need? And I mentioned that already before. There is no, I'm not aware of a paper that thoroughly assessed that. The rule of thumb is 10, 100 random steps. The more random steps you have, usually the better. That brings numerical stability. But it also means computational burden. So that's a little bit of a trade-off. I wouldn't go below 10. And an easy way to check that is if your analysis is reasonably fast, then just try a few different value for the random steps. You could try 10, 50, 100, 200. And if the coefficients stabilize, so if there's no more change in the coefficients, then you probably reach the point where you have a sufficient large number of random steps. Okay, the take-home points here is that you can extend a step selection function to include movement. That's then the integrated step selection function. What we do is with sample step length and turning angles from a statistical distribution that was fit to the observed steps, but not anymore. We don't use just the observed steps. And then we can include a function of step length and in the model. That was like a really fast tour through integrated step selection functions. If there are questions, I'm happy to answer them. I put in a few publications that I think might be helpful. So the one from Tal Afkar, where he introduced the integrated step selection function, is very good, together with the one from James Forrester. They're both a little bit technical. Then John Feeberg published last year a paper on interpretation of parameters. So that's very useful, I think. Stephanie Muff published 2 years ago a paper on how to account for multiple individuals. So what I sketched out now was really the case if you have one individual, if you have one fish, that's usually very unrealistic. And as soon as you have more than one individual, it becomes kind of challenging, or we have to think a little bit about that. And so Steffi highlighted that here. Then this paper by Henrik Thürfjell is a really nice and approachable introduction to step selection function. And then I, together with John and Tal, I wrote a paper in 2019 where we introduced the AMT package and where we also go through some practical examples. So, are there any questions? Maybe I do that now, or we could just move to the practical and hoping that will make things a bit clearer.
Johannes, I cannot see any questions here or on the internet, so I guess that you can proceed.
Okay. So, I prepared a small R script, and where we do that, where we run through an example. So Henrik, I think is also here.
Yes.
Allowed me to use some of his data on pikes. So thanks a lot for that. I want to stress again, so I'm not a fish biologist. I just tried to make up something. I'm not sure if it's biologically meaningful, but I hope it will illustrate the case. So I'm not going to go on to biological interpretation, but hopefully it will still make sense. So we need a few packages here. So the AMT packages is the one that I'm working on, animal movement tools, where we implemented step selection function, but also other things. And so the step selection functions, they're not that difficult, especially because we can use conditional logistic regression, and the survival package provides us with conditional logistic regression, very good implementation. But getting the data ready can be a bit tedious, and that's the steps that we tried to make here a bit more approachable. So I used here, I set a seed because we have different, we'll take random steps, and in order to make that reproducible, I put a set seed here. Okay, so we need covariates for that, and Henrik provided me at some point with a lake, with a shore, and I thought maybe an interesting covariate for that would be the outline of the distance to the shore. So I'm sorry, it shouldn't be like that, but it doesn't matter. So to do that, I used a raster package. I first create a raster that is has a 5 meter resolution and covers basically this whole area. I then rasterize the lake, and I do that a little bit the other way around. So I say I want the background value of 0. These are all the pixels outside the lakes. They get a value of 0. And the field, so that these are all the pixels inside the lake, I set to NA. The reason why I do that is that the distance function from the raster package will take all NA pixels. So these are all the pixels inside the lake, and calculate the distance to the next non-NA pixel. So the next non-NA pixel is the pixels on the shore. If you do that, it should take a few seconds, but not too long. Then we get the distance to the shore like this. But I intervened here with an additional step, and I mask. So the mask function makes everything outside the shapefile of the shore as an A. So that's everything that's out here. We'll need that later to be sure that points that are not in the lake can be removed. So that would be our covariate. You could include many more covariates, and the way to do that is you prepare them all in the same way, and either you create a raster stack if they all have the same resolution. If they don't have the same resolution, then you would have to create separate rasters and call them time to time later on. Then we are off to the telemetry data. So there's I didn't do any data cleaning, so I think you talked about that in the previous days already. So make sure the data that goes in here is at least clean in terms of the positions. And there are 52,000 relocations. To make everything a bit faster and for the purpose of this training workshop here, I decided to just use the first 25,000. So I subset just from 1 to 25,000 here. And that's what this data set looks like. I'm mostly interested in the timestamp, in the X, and in the board. Now we need some data preparation to get the tracking data in a suitable format to fit a step selection function. Well, I start here. So I start here selecting just the relevant columns, which is not strictly necessary, but sometimes it's useful to do. I then use, so I guess most of you are familiar with the pipe operator. Yes. So you just pass the result from here to here to here, and you conduct different functions on the result over and over again. I then created a new column called timestamp, and the timestamp here, that was just a character. And you can parse then the timestamp with this year, month, day, hour, minute, second function from the lubridate package, and then R knows it is a timestamp. It's a date or a timestamp, and it's easier to work with that. And then we can use the function make track from the AMT package, and it needs at least an X and a Y coordinate. Everything else is optional. If you want to fit a step selection function, we need an X, a Y coordinate, and a timestamp. And we could also include additional columns. I didn't include any here because there wasn't anything that we need. But for example, if you have multiple animals, you probably want to have a column called ID as well. And then I finally included a coordinate reference system here. It's a good practice to include that, but if you're tracking data and your covariates and are in the same coordinate reference system, then you could also leave it out. Okay, so then I do that. If we plot that one, then you see that's the lake again, and this pike was in this first 25,000 vegetation were just around this northern corner. Now we don't know anything about the sampling rate. So how often did we observe this one fish? If we use the function summarize sampling rate, it does exactly that. We get a summary of the sampling rate, and we see the minimum sampling rate as well as in the sub-second, an order of magnitude of sub-seconds, and it goes up to 8.5 minutes or so. So the units are minutes. We have a median and a mean sampling rate of 1.5 minutes, so 90 seconds. Now, the question is, what is a meaningful scale here? Time scale for step selection functions. So I would argue that going below probably 10 minutes or something like that, that's just a gut feeling, is probably not very meaningful because the availability will be very, very constrained. And then you also reach the limits of what step selection can be useful for or not. I decided to go to a 30-minute sampling rate, also because it makes everything much faster to fit for this workshop, but you could also go maybe to 10, 20 minutes, but you just have to think about that a little bit beforehand. The function track resample allows you to resample a track. So we're not doing any interpolation or anything. We just take the data that is here and we try to resample it to every 30 minutes, and we give a tolerance of 90 seconds. So the minutes and seconds function, they come from the lubridate package, and it just allows you to create a period object that the track resample then can work with. Of course, it's a pity to do that because there's so high resolution data, and then we downsample that. But if you have such good data, then depending on the questions, but probably for some questions, step selection function might be not the right method. If you look at this again, well, surprisingly, the pike still stays in the north corner of the lake. Everything else should be a little bit worrisome. But we have we drastically reduced now the sampling rate. Okay, so now we have data that we think we can work, tracking data that we can work with. If you look at this ones, we have an X, Y, and a T coordinate. That's what the AMT package added for us when we created the track. Basically, it's the XY before, but the standard notation in AMT that is that we always have an underline here to note that you shouldn't manipulate that anymore. Of course, it's R, so you can manipulate it, but you shouldn't. The track resample then created a new column called burst underline, and the burst underline column is telling us in which burst each observation is. And you can think of a burst as a series of points with constant sampling rate. So everything in burst 1 is separated by 30 minutes. As soon as you have a gap in your data, for example, because the device failed, maybe your device was programmed such that it does not record the position during the night, then you would have for each day a burst, then a burst would occur. The nice thing about step selection function is that it doesn't care if there are steps breaks in there. So if your device, if you have separate chunks, separate bursts, then you can analyze that happily with step selection functions. There is a function called filter min and burst. So that means to just retain bursts with a minimum numbers of observations. Here I said the default is 3, so that means we would have to have at least 3 observations in a burst in order to be retained. The reason behind that is if we have less than 3 observations, we can't calculate a relative turning time. Then we are moving from the step representation to the burst representation. The function steps by burst will do that. And then we pair each step here. Sorry, I just wanted to execute it because it takes a while with 100 control steps. So I said I'm not sure. I said before there's no rule of thumb how many control steps there should be. Here we have the additional difficulty that we are in a lake. So there's nothing that prevents R from taking control steps outside the lake, but we have to remove them afterwards because they're biologically unsensible. The random steps function now takes our steps object that has a column with the step length and the turn angles. It fits a gamma distribution and a von Mises distribution here, and then pairs each step with 100 random steps where it draws the step length from the fitted gamma distribution and the turn angle from the fitted von Mises distribution. Okay, then the next thing that we can do is we can start to annotate these steps, to put some covariate value to each step. So the first one is that we add the time of day. That means was a step, did it end or started during the night or during the day? So if the data is protected, that means if we added a coordinate reference system, R will figure out automatically where you are, and then using from the SP package the function to calculate the day length, and then figure out if you're if it's during the day a step or during the night. The argument where lets you modify if you want to ask for the time of day at the start of the step or at the end of the step. I put both here, so we have the time of day for the start and for the end of the step. And the same here with extract covariates. So we extract the covariates for the shore distance at the start and at the end of each step, again controlling that with both. If we would have a raster stack, so many raster stacked on top of each other, we could replace shore distance with the raster stack here. We could also have multiple calls to the function extract covariates, for example, if we have rasters of different resolutions. I then did a manual encoding, dummy encoding for the categorical covariates time of the day. So if it's, and just put it as 0 and 1 if it's at night or during the day. This makes it easier than with the model fitting. So so this is exactly the object that we get out. We have these are steps. We start here at x1 and y1 and go to x2, y2. We have a step length. We have a turn angle, not in the first step, but in all consecutive steps. Then we have the time when the step started and ended. dt is the time difference. And here are all the covariates that were used in this model. Now, the next few lines here, I'm not going to explain it in great detail, but basically what they do is they check how many steps are outside the lake. And so you see for it varies by up to 50 steps that could be outside the lake, but that only occurs once. And what I then do is I remove all the steps that end outside of the lake and resample them, take a sample of 20 of all the steps that are inside the lake, so to overcome that problem. Right, and then we have to put them together again. And now we're in a position where we can fit a model. This app. I came up with 3 different models here. The first model is really just habitat selection, and I didn't put in the preparation, I forgot to set a proper name for distance to shore. So distance to shore is just called layer now. Sorry about that. And I say the case. The case is the variable that indicates, are you an observed step or are you a random step? And I say whether or not the variable is a case or not just depends on the value of the step at the end. And I have to provide the strata, and the strata is the step ID. That means the first observed step paired with its 20 random steps forms strata 1. The second observed step paired with its 20 random steps forms strata 2, and so on. We do that, that's relatively fast. We can fit first model. In the second model, now also included a covariate for proof. And that's the step length. So how long was that step? And that was and I even included an interaction between the step length and the layer. That's the distance from the shore. That why did I do that? One could model here, is the animal moving faster or slower at different distance from the lake? And in a final model, in a third model, I extended that and included also time of day, or if a step is ended during the day or during the night. So we could, one hypothesis that we may want to test is animals prefer different distance to shore during the day or during the night. Okay. So there are different ways then how we could compare this model. AIC is one of them, certainly not the only one. Using AIC here, we get some support for using the most complex models, so suggesting that day of time of day does as. That's correct. Okay, I'm not gonna. We could look at all the models here as we get used to it, and we get a summary here. I'm going to skip on that and move directly to using the log RSS or RSS. RSS is the relative selection strength. There is a paper that introduces that, the RSS. I linked it here. That's the one. That's one that Tal wrote a couple of years ago, and then there's the one paper from John on the how to do interpretations for habitat selection models, and there's especially supplement B and C. There are very detailed descriptions how you could do that. So the basic idea is that we create two steps, or sorry, not steps, 2 points in space where we think the animal could go, and then we compare these points relative to each other. So, and to use the log RSS function, we have to create two data frames. So data frame 1, we say the distance to shore is 5 meters. It's during the day, so night is 0. 1 would be it's during the night. And location 2, we say that the distance to the shore is 100 meters, everything else being equal. If we then execute that, and we calculate the log RSS, it returns us a list with a data frame, and there's a column called log RSS.
Johannes, can you hear us? I think it's, I would say that it's just on Johannes' side, so just let me check.
Maybe you can ask other participants if you are still. Other participants, can you hear us?
Yes? Philippa? Ah, Johannes is back. Okay.
But no sound?
Johannes, we lost you for a second, and you are muted right now.
Yeah.
Sorry.
Sorry, my Teams just closed.
Ah, okay.
Okay, but you can hear me again?
Yes, but we can see your screen.
Yeah, I forgot.
Please run the share screen one more time.
Yeah. Okay. Sorry for that short break. So we were here at the RSS, so the relative selection strength, and a value of 1.5 means it's 1.5 times more likely to move for the animal to observe that position that is closer to the shore than to the position that is farther away from the shore. We can do the same thing, for example, by comparing two positions that are now at the shore, but position one is at night and position two is during the day. And if you do that, we then see, well, there is no difference. We get a log RSS of 1. And I just see here that there is that they wrote something different here. I will have to double check that. Now it becomes more interesting if we investigate a whole range of values. So for x1, we could say, well, the distance to shore that we observed in the data set are between 0 and 300 meters. And it could be either during the day or during the night. And we then choose one reference position that's 100 meters away from the shore during the day. And I can calculate this log RSS for all of this position at once. And I can even get an uncertainty estimates using standard errors here, or you could also bootstrap if you prefer that. And this can then be easily be plotted using ggplot, for example. And what we see here now are two lines for the log RSS. Data exponent. No. So this is the reference position here. You see that because here the line goes through 0. That's during the day, and at position 0, 100 meters away from the shore. During the day, that's the red line. Position closer to the shore are preferred relative to the position 100 meters away from the shore, and positions farther out in the lake are avoided for that one fish. During the night, we see an opposite pattern, and that is that positions closer to the shore or the pike may choose positions that are further away with a higher preference to positions that are closer to the shore. Right, so that's the habitats part. And the movement part, we can also look at how did movement change, because we included the coefficient for the step length of steps. This becomes a little bit tedious, and you have to be careful that you don't lose a term somewhere. But the gamma distribution is parameterized using two parameters, the scale parameter and the shape parameter. The scale parameter is linked to the coefficient of the length. The shape parameter is linked to the coefficients of the log of the step. I only included the coefficients for the step length here. And we can now calculate a new scale parameter, an adjusted scale parameter, for each combination of distance to shore and time of day. So whether it's during the day or during the night. So that's what is being done here. And then you may know that the mean, so the expected value of a gamma distribution, can be calculated if you multiply the shape times the scale parameter. So I can do that here and calculate expected displacement. And if we create a plot again here, we can see that there is a difference between the expected displacement between night and day. So the model suggests that fish move more during the day than during the night, but there is no real effect of the distance to shore. So you see there's a slight negative trend that if fish are further away from the shore may move less, but I don't think that's anywhere near statistical significance, but we could double check. Right, so that's a very, very simple model because we didn't bother about turn angles. If you have more, if you would use every 10 minutes or so, probably turn angles would become much more interesting. But the model, we would then have to add to the model the cosine of the turn angle, because that's a modifier of the concentration parameter of the Van Mises distribution, which controls how concentrated the turn angles are. So if the concentration parameter is very high, you're very likely to go off in the same direction. If it's very low, you're very likely to make the turn maybe off without or without any predictable direction. Okay, I think that's a very quick talk through to a simple example using one fish. And I think I'm happy to take questions if there are, should there be any.
Do you have questions for Johannes?
Yeah.
Yes.
I was wondering, once you've done that with one fish, how would you do that with multiple fish and test, for example, the effect of length on habitat selection or something like that?
So you mean the effect of fish length?
Yeah, if I had, say, 10 fish, could I run the model and, yeah.
Okay, so there are multiple ways you could do that. So you could, for example, fit an individual model on each fish, and then do some statistics on the coefficients. So we did that, I think, in the 2019 paper where we introduced AMT. So you basically just take the coefficients of each fish and then plot that against fish length for different fishes. Or if you want to, you could move into a more statistically a bit more challenging exercise. If you use the fixed effect, the random effects model, then you can include different fish. So you could include the length of the fish as a fixed effect, for example, and then use an interaction for the terms that you hypothesize that may change or that are affected by the length of the fish, and then directly estimate this coefficient.
Okay, thank you.
You're welcome.
No, I cannot see any. Yes, Anna?
Hi, Johannes. Thank you for this talk. It's very clear. My question was, can you also include some kind of social information in those models? For instance, like the distance to other individuals or something like that, also to see if the movement depends on the distance to other individuals.
Yes, yeah. In fact, there's a paper by Ulrike Schlegel, which you may or may not know. I can add that to the presentation, and she figured out a way how to kind of interpolate simultaneously where the other individuals are, and then use that as an additional covariate, and then you could model avoidance or attraction or neutral behavior towards other individuals. So that it's a bit tricky, but it's doable.
Okay, thank you.
Other questions?
if the questions come up later, then do feel free to email me. I understand that was quite fast now, and probably if you're exposed for the first time, a bit hard to follow.
Yeah, Johannes, it seems that we somehow lack more questions. So we would like to thank you very much for your talk.
Yeah.
Hello.
Actually, there is one late question. Okay, Mauricio, go ahead.
Yes. Sorry if I was slow, but I couldn't find the hand.
That's okay.
Okay. It's just a curiosity, and it's about verifying the quality of data. I mean, for example, at the very first part of the exercise, we calculated the distance from each pixel to the shoreline. But is there a way to see those data? I mean, to verify if they are they have like a good pedigree. I mean, like I imagine that from the center of the lake to the shoreline, it's 3 kilometers. But if I visualize the data and I see 300 kilometers, I may have done something wrong. So is there a way to visualize numbers? Like,
Yeah, I'm not sure if I understood you completely right. So
we can move to line 35. Yeah. Here we calculated the distance from the shoreline. Yep. Okay. How can I visualize the unique values?
Okay. So first of all, the distance to the shoreline will be a bit. It depends on the resolution of my raster, and I just set it to 5 meters here because I didn't want the analysis to take too long. So if you would do that for real analysis, you probably want to move down to 1 meter. If you want to see just the unique values of that raster, you can do it like this, and you. Well, that is. We have to use the shortest. So these are all the unique values now that you get. Is that what you were asking?
Yes, thank you. This was important because it happened at different rasters. You try to calculate the distance from shore, but you find unexpected numbers, and you know, then during calculation and stuff, they pop up. So I didn't know how much.
Excellent. Okay.
Okay, if there are no more questions,
Then have a good reminder of the workshop.
thank you, Johannes, for sharing an hour and something with us, and for your preparation for your talk. Thank you very much. Okay.
Thanks for the
input. Bye.
Bye.
Okay, guys. So I guess that we can go for that group photo.